Hi everyone, in this video I'll be doing Advent of Code 2021, Day 22. I'll be doing the puzzles, then explaining them afterwards. If you'd like to see my code, it will be in the description, so check that out. And let's get started with the puzzles. Alright, time to explain the puzzles. So I think today's puzzles were quite difficult, mostly part 2, because it required a bit of extra thinking and reasoning with examples that was quite complicated. So, for part 1, we are asked to reboot a reactor by turning on and off a series of cubes within a three-dimensional space. So this space consists of a bunch of cubes in a grid, and we have these steps to turn on ranges of cubes or turn them off. Our task is to find the number of cubes that are on after doing all of these steps, but only the steps that are within the range from -50 to 50 for every x, y, and z coordinate. For part 1 at least, this means we can bash it out. We can directly simulate it by keeping track of a grid. In this case, I'm using NumPy grid, just using a three-dimensional array of 101 by 100 because the indices go from -50 to 50. So I'm actually converting those to a range from 0 to 100 inclusive. And then after that, for every step, I'm just turning on or off all of the cubes inside a given range. And then after doing all the steps, we just have this three-dimensional array, and in it we can count the number of on cubes, which is our answer. And if you want to check out this code, it's in the description below, so don't worry if you don't get it all right now. Alright, so part 1 is pretty simple, comparatively. Part 2 is now much more difficult. So, in the inputs, we are not just restricted to the range -50 to 50 now. We are given big numbers up to tens of thousands. So, the question is now, after doing all the steps, how many cubes are on inside this grid? And the answer can be quite large, so we know that we cannot directly simulate it. We have to do a bit of extra thinking and smart stuff. But first of all, full disclosure, I got part of my solution from a solution on the subreddit, so these ideas are not completely mine. I got some help along the way. But here's how I did part 2. So first of all, we need a way to work with cubes, and these aren't actually cubes, they're cuboids, they're like boxes, but I'm just going to say cubes sometimes because it's easier to imagine them as cubes, but you'll know what I mean. So we have these two functions right here. They take in this first one, computes the volume of a cube, and we're representing cubes here as an array or a tuple in Python of 3 different bounds, and each bound represents the x and y, the min and max of each range. So for example, in the example they give this cube, which I'm representing as this. This is just the cube that goes from 10 to 12 in every dimension, and it kind of looks like a Rubik's Cube. So 3 by 3 cube is going to be represented like this. Of course, we can extend this, so if it was 9, 12 for the y coordinate, this would instead be a 4 by 3 by 3 cube, which just looks like that. So given a volume, we just have to find the length, width, and height of the cube, and making sure to add on 1 because, like 10 to 12 is 3 cubes, not 2, because 12 minus 10 is 2. So we have to add 1 because we have to include all the cubes inside the range. So that's a bit about how I'm representing cubes as well as how we compute the volume of a cube. Now, we have to find the overlap between 2 cubes. This is going to be essential to our solution. We have 2 cubes here. How are we going to find their overlap? Well, we're going to do this on an axis by axis basis. So we're going to do it on x axis, y axis, and then z-axis to make it a bit easier to think about for us. So I didn't draw this super well, but if we just consider the x-axis, it might look something like this. Something like that. That's cube 1, and this is cube 2. Actually, maybe I won't draw these horizontal lines. So this is x1 and x2, and this is... maybe I should index these better. I'm using B to represent bounds because that's how I'm representing cubes. So let's suppose we have this. This is just the slice of the x-axis. I'm saying x-axis, but it's like just the x coordinates. We have these 4 lines, and in theory they go like infinitely far. We don't know the ranges of the y coordinates or the z coordinates. So this is a flat plane, and we have 4 lines here which are just an x coordinate. These first 2 lines on the left are the bounds of the first cube, and these 2 bounds on the right are the bounds of the second cube. So how do we find their intersection? Well, first of all, let's find what their intersection is going to be. Their intersection is going to be right here, between these 2 lines, right? Because, if you think about it, you layer 2 things on top of each other, that's just what it's going to be. That's going to be this area in between. So the new bounds for their intersection is going to be b2, 0, comma, b1, 1. Now, how do we find this? Well, first, we have to recognize if these two cubes are not intersecting at all. And that would happen in a case like this, if the bounds looked like that, and the other two bounds were completely on the other side. So if the min of one of the bounds is less than the max of another, if the max of one of the bounds is less than the min of the other, then they're not intersecting. Or the other way around. So if we had these two swapped instead, and this one's max is less than this one's min, then it wouldn't count as well. So if for any of the axes they don't intersect, then we know they don't intersect at all. Now we look at the case where they do intersect. If this is discarded, if this is not intersecting, let's look at the other case. So now we know they must be intersecting. We look at the mixing up of the min and maxes of these two bounds. So we take the max of their lower bounds, and we take the max of their lower bounds and the min of their higher bounds, and somehow that works out to give us this middle range over here. And if you think about it, the lowest possible lower bound is not going to be part of this range, and the highest possible upper bound is not going to be part of this range. So we just take the other ones, and that gives us our bounds for the intersection. Yeah, I just had this check here. This is not necessary. And then we can just append the bounds to our final overlap cube, and that just gives the overlap cube. All right, so now that we've got our two functions for working with cubes, let's actually solve the problem. So the key idea in this solution is to keep track of different cubes, which are going to be either intersections between two other cubes or cubes in and of themselves, and keep track of the counts of this number of intersection. Because if you think about it, there's going to be a lot of overlaps, and they're going to be hard to count. So we're just going to be keeping track of all of the possible intersections between two cubes, and how many times we should count them. If you're familiar with math and combinatorics, then you know this as the principle of inclusion and exclusion. And then we're just going to be doing a programming way of doing that. So essentially, let's look at a Venn diagram. All right. I think this might be the best example. So we have cube 1. All right, I'm just going to label this C1, C2, and C3. We want to make sure, let's assume all of these are adding. So we want to turn on all of these cubes within this range. And I'm representing this, of course, as a Venn diagram, so these are not cubes. So how many times do we want to count everything inside here? Well, we want to count it once. So we're going to add C1 right here. Same for C2 and C3. So we're going to add on C2 and C3. So this is just saying that all of the cubes inside C1, C2, and C3 should be on. But now we have a problem, right? Look at all the cubes inside here. They are turned on twice, but we only want to turn them on once. So what we need to do is find the intersection between C1 and C3 and turn them off. So we actually need to do C1 intersect C3. So this is the symbol for intersection, and turn that off. So we're subtracting this from the total to make sure that these are only counted once, because we overcounted them. Same for C1 and C2, and same for C2 and C3. But now we have another problem, which is that this section in the middle is now counted 0 times, and we want to count it once. So we need to add back this critical intersection in the middle, and that gives us our final answer. We are now counting every single region exactly once, and that is what we want. Now, how do we extend this to our actual problem, right? So we're going to be keeping track of essentially the same thing. We're going to be keeping track of same like C1, C2 stuff, and we're going to add a sign, either a +1 or a -1 to that, and we're representing this as a dictionary. This dictionary takes in a cube as the key and stores its sign, actually its amount, because we might be subtracting 2 or adding 2 or subtracting 3 at some point. So we're actually going to be keeping track of that as well inside this dictionary right here, or map. So that might look something like this in this example. We would have C1 being 1, C2 being 1, C3 being 1, and then C1 intersect C2 being -1, and so on, and then C1, C2, C3 intersect being 1. So that is what our dictionary might look like. Now, how we're going to do this is consider we already have something for the first n cubes, right? We have a bunch of intersections, and everything is being counted exactly once as we wanted. Now, this is just like a black box, right? So now we add on a new cube, right? This new cube, I'll draw it in a different color, right here. Now we want to count everything inside this new cube exactly once as well, and not do any overcounting with the previous sections. So how we're going to do this is we're going to look at all the intersections with all previous cubes, no matter their sign, and we want to reset them to 0. So this intersection right here, reset it to 0, all right? Everything inside here should be counted 0 times. Same for here, so that everything that has an intersection with the previous cube of previous cubes with the new cubes, all of this gets reset to 0. And that is what these lines over here are doing. We are simply counting the number of times that that intersection has been counted, and we are resetting that to 0. So all the cubes inside this blue range right here, they're now being counted 0 times. And after that, you might realize that we can't count them 0 times, so we have to add back 1 time for the new cube. So after we reset those intersections to 0, we add back 1 for the red cube, so that everything is counted once, as it should be. So essentially what we're doing here is we're just accounting for overcounting, resetting all intersections with previous cubes back to 0, and then adding 1 to them using the new cube that we just added. So if you want to see this code, it's somewhat complex, but it'll be in the GitHub repository, so check that out. This process works with both positive cubes and negative cubes. It's just that if this red cube is instead subtracting, then we simply delete all the intersections, so we subtract 1 from their tally. We reset them to 0 for their tally and don't add it back. So you can notice we're only adding the red cube if it is an on operation. And otherwise, we're just turning every intersection with previous cubes back to 0, so we're counting them exactly 0 times. Notice that we do have to do this simultaneously. We cannot update our dictionary as we are reading our dictionary, so of course we're making a new dictionary to update the counts so that we can do it all simultaneously. So in summary, we are keeping a giant dictionary of cubes, and in this case, these are individual cubes, not intersections of anything, so we will actually compute these to store in the dictionary as opposed to storing them as simply intersections. We have this giant dictionary keeping track of how many times each range should be counted. Every time we add a new cube, we are removing all intersections with previous cubes, we're resetting them to 0, so that when we add on our new cube, if it is on, then everything inside it is counted exactly once. And at the end, that makes our computing of the answer very simple. We just have to loop through all the cubes that we counted and add them on according to their sign, or like exactly how much they're counted. So either -1, +1, -2, +2, etc. And that's where also our handy-dandy volume computation function comes in. Alright, so that's it for Advent of Code 2021, Day 22. I think today's puzzles were quite difficult, especially part 2 again, so don't worry if you had a challenge solving them. I hope this video was helpful. If you want to see the code, again, that's in the description. And I just want to say thank you for watching, and I'll see you tomorrow for Day 23.